Okay, so continuing to go through the problems from our midterm exam, question 4 tells us that natural samples of carbon are made up of a mixture of carbon-12 with an atomic mass of 12 units exactly, and carbon-13 with an atomic mass of 13.0034 units. And then using the average atomic mass of carbon given in the periodic table, we want to determine the percent abundance of carbon-13. So first of all, we're going to need to look up the average mass, average atomic mass of carbon, and that's in the periodic table, and it is 12.011. And so in order to work out the percent abundance of carbon-13, I'm going to let X represent the fractional abundance of carbon-13. We could let X represent the abundance of carbon-12. I just chose to let X be carbon-13 since the abundance of carbon-13 is what I'm actually trying to find in this problem. And so it'll be easier if I just let X equal that directly. And then since the fractions of the two isotopes add up to 1, if the fractional abundance of carbon-13 is X, the fractional abundance of carbon-12 will be 1 minus X. And so then with these expressions for the abundances, the average atomic mass in units of the unified atomic mass unit U for carbon is going to be the contribution from carbon-12 plus the contribution from carbon-13. And so we'll have 1 minus X times 12 plus X times 13.0034. And that all adds up to the average atomic mass of carbon, 12.011. So multiplying out the left-hand side, we get that 12 minus 12x is 13.0034x, and that's still 12.011. And then subtracting 12 from both sides and simplifying on the left, we get 1.0034x is equal to 0.011. And so solving for x then gives us x is 0.011 divided by 1.0034, or 0.0109627. And so before I convert that to a percent, I also want to worry about the rounding this off to the right precision. So the numbers that went into the calculation, the 12.011 has 5 significant figures. The 13.0034 has 6 significant figures. The 12, the atomic mass of carbon-12, that's an exact number, so that doesn't have significant figures. Or I suppose you could think of it as having an infinite number of significant figures. And likewise, the 1 in 1 minus x is an exact number. So the two numbers that affect the precision of our answer have 6 significant figures and 5 significant figures. So at first blush, it might seem like we should take the lesser of those and round off our answer to 5 significant figures. But there's an extra little bit of trickiness here, and that comes about because in the process of solving this problem, we ended up doing a subtraction. And subtraction does funny things to the precision of numbers. When you subtract two numbers, you often lose precision, and that's exactly what happened here. And specifically, when you look at just before we divided to find x, we had 2 significant figures in this number here, the 0.011. And so when we do our division and we're dividing the 0.011 by 1.0034, you're dividing a 2 significant figure number by a 5 significant figure number. And so the final answer is only going to have 2 significant figures. And so rounding that off and converting to a percentage, we get our answer of 1.1%. So one take-home message here is that anytime subtraction occurs in a problem, you need to be extra careful with your precision, because subtraction almost always leads to a loss of precision, and so you just have to watch out for that, because it can kind of bite you if you're not a little careful. Okay, so problem number 5 says that the initial design of the Mercury space capsule in the late 1950s included a 600-pound heat sink made of solid beryllium. And in part A, using 2.20462 pounds equals 1 kilogram, we want to find the mass of the heat sink in kilograms. And in part B, we want to calculate the volume of the heat sink in cubic meters. And we're given that the density of beryllium is 1.85 grams per cubic centimeter. Okay, so for part A, we've got our 600-pound heat sink, and we want to convert that to kilograms. So we're going to put in a conversion factor where we divide out the pounds and multiply kilograms. And the numbers in that conversion factor are 2.20462 pounds are equal to 1 kilogram. So when we multiply this out, the pounds will cancel, and we'll be left with kilograms. And specifically, we get 272.156 kilograms. And then we do want to round this off. So 600 pounds has 3 significant figures. Our conversion factor has 6 significant figures. The 1 is an exact number, so that doesn't affect our precision. When you multiply and divide numbers, the lesser precision going into that will determine the precision of your answer. So in this case, we'll round off our answer to 3 significant figures, and we get 272 kilograms. Okay, for part B, we want to find the volume of the heat sink, and we're given the density. Density allows us to relate the mass to the volume. We just found the mass of the heat sink, and so by using the density, we'll be able to find the volume. So the density was 1.85 grams per cubic centimeter, so that tells us that 1.85 grams of beryllium has a volume of 1 cubic centimeter. And we do need to be careful here because in this conversion, in the density here, we've got the mass in grams, but the mass that we calculated was in kilograms. So we're going to have to be careful to convert from kilograms to grams. And then the volume in the density is in cubic centimeters, and we are asked for the volume in cubic meters. And so we're also going to have to do a conversion there. So we've got our mass, 272 kilograms, and rather than using 272 kilograms to calculate part B, I'm going to go back to the value before I rounded it off, 272.156 kilograms. And this just, in this way, I avoid introducing any error due to the rounding off from part A. So I've got my number of kilograms. I first need to convert that to grams before I can use the density that was given. So I'm going to want to convert from kilograms to grams. And we do that knowing that 1 kilogram is 1,000 grams. So now the kilograms will cancel. And then I want to convert from grams to cubic centimeters using the density that I've got. And specifically, we were told that 1.85 grams is equal to 1 cubic centimeter. So now our grams will cancel. And finally, we want to convert from cubic centimeters to cubic meters. And we need to be a little careful here. We know that there are 100 centimeters in a meter, but here we're dealing with cubic centimeters and cubic meters. And so the relationship there is not simply 100 to 1. 1 meter is equal to 100 centimeters. And if you cube both sides of this relationship, 1 meter being cubed is equal to 100 centimeters being cubed, because 1 meter is 100 centimeters. And then cubing both sides, expanding out both sides of this relation, we get that 1 cubic meter is actually 1,000,000 cubic centimeters. It's 10 to the 6. So we've got 10 to the 6 cubic centimeters are 1 cubic meter. And so now our cubic centimeters will properly cancel, and we'll be left with cubic meters. Multiplying and dividing, we get our volume is 0.147111 cubic meters. And for our answer, the mass that went in Even though I wrote it down with 6 digits, it does only have 3 significant figures because that number in turn was based on a precision of 3 significant figures. And then our density has 3 significant figures. And all the other numbers in our conversion factors are exact. And so we're going to want to round this off to 3 significant figures. And so well, that will give us a final answer of 0.147 cubic meters. Okay, and I'm going to end this part of the video here, and we will continue in the next part.